Okay, now we're going to talk about a bit more real-world problem using vectors, talking about relative velocity. Now, in this particular case, we've got a plane that is flying northeast at an airspeed of 563 kilometers per hour, and we've got a wind that is blowing to the southeast at 48 kilometers per hour. So what's happening in this problem is that while the airplane is flying in one direction, the wind is pushing the airplane off course. So the pilot, once he or she realizes what is going on, has got to make a correction and make a change. Now, if you don't think this is a real thing, look on YouTube and you should find several videos of airplanes. Okay, look on YouTube for airplanes landing in a crosswind. Seriously, winds can get strong enough they'll knock a 747 off path. So in this case, we've got a plane. It is flying north of east, or northeast, which means it's flying at a roughly 45-degree angle. Oops. So it's flying at roughly a 45-degree angle to north. Okay, hold on. I'm going to add the 45-degree angle in there. Now, I'm not going to worry about drawing the distance to scale. All I'm trying to do is give you an idea of what's going on. But the wind itself, and in order to do this part of the problem, I'm going to have to add another coordinate system right over here. So we've got our original coordinate system for the airplane at the starting point. And now we have our new coordinate system. Okay, so while the airplane is flying northeast, the wind is pushing southeast. I'll go ahead and plug that in right there. And again, that's at a relatively 45-degree angle. Okay, so I'm going to put my two vectors in here. So we've got the first vector, 563.0 kilometers per hour north. Okay, then we got our other vector. Let's stick that in here over here. 48.0 kilometers per hour. Okay, the first one was 563 kilometers per hour northeast. The other one is 48.0 kilometers per hour southeast. So we started out, our airplane was going in one direction, but the wind is knocking that airplane off course. I'm going to try and draw this at a much more pronounced angle. Okay. So, northeast and southeast. Now, if you'll have noticed, because this is a 45-degree angle right here, then this is going to be a 45-degree angle right here. What we have here is a transversal. Then we have another 45-degree angle going down here, and again this is like a 90-degree angle right here. So what we really have is a right triangle, nice and easy to deal with. Okay, now we know that this is 45, so we know that this total angle is 45. That's going to be important in a minute. The entire angle is 45, but we're trying to find two things. We're trying to find this angle here so that we can determine what this angle is. I'm going to put a different value here. But we also want to know the vector. So I'm going to worry about the vector first. Now, if you recall, if you have a right triangle, if you've got like a right triangle problem like we have here, all you need to do is figure out the hypotenuse. So your new vector is just simply the hypotenuse of this right triangle. Now, if you remember our formula for the hypotenuse is equal to the square root of the opposite side squared plus the adjacent side squared. We know the opposite side, 48 kilometers per hour, so I'll go ahead and plug that in, 48 squared. And then the adjacent side is 563.0 squared. Okay, both of those are in kilometers per hour, so once we square them and then take the square root, we're going to end up with kilometers per hour as our magnitude for the vector. Now I'm just going to go ahead and plug that right into the equation. So 48.0 squared added to 563 squared, okay, end up with a rather larger number than we should be getting. You just need to remember to take the square root, and the punchline is 565.0 kilometers per hour. Okay, so it turns out the airplane is going a little bit faster than expected, but the problem is the airplane is off course. So to figure out what that new course correction is going to be, because if you remember, if the airplane is off course, the airplane is going to have to change its direction in order to get back on course. And if you don't think course correction is that big a deal, this airplane is most likely going to run out of fuel long before it reaches the airport it was aiming for, unless it makes an air correction. So let's figure out what the actual heading or the actual bearing of the airplane is so that the airplane can make that course correction. All right, so now we're going to be using our tangent function. Now, if you remember, tangent of theta, that's a really awful theta, sorry about that, is equal to the ratio of the opposite side over the adjacent. So in other words, theta is equal to the inverse tangent of the opposite over the adjacent. So I'll go ahead and plug that in. Inverse tangent of the opposite side, which is 48.0, divided by the adjacent side, 563. Okay, so we'll go ahead and plug those numbers in. That is 48 divided by 563. Then on my calculator, I now need to hit the inverse tangent to get what looks like a very small angle, 4.87. Remember, 3 sig figs, 4.87 degrees. So the airplane is 4.87 degrees off course, and let's figure out what his actual bearing is. Now, if you recall, this entire angle is a 45-degree angle, so to figure out the actual bearing, we want to take 45 degrees. I'll put a 0.0 in there so we can keep our correct number of significant figures, minus 4.87 degrees. So let's see, 45 minus 4.87, and we come up with the value of 40.1 degrees. So the total vector that our airplane is actually going is 565.0 kilometers per hour at 40.1 degrees north of east. Now that your airplane knows the actual vector, our airplane can make the correction and get back to where he belongs, and that is sample problem F.